Welcome to part 2 of Applications of Number Theory. In this part we'll be looking at some background information in linear congruences leading up then to the Chinese remainder theorem. We turn now to page 4 of the notes and take up the topic of linear congruences. Linear congruences are statements such as these: 2x is congruent to 5 modulo 7 and 2x is congruent to 3 modulo 4. In both cases, our goal is to find a value of x that will make the statement true. Now, let's suppose that we take the first one, 2x is congruent to 5 modulo 7. Well, when we're working modulo 7, there are only 7 congruence classes, 0 through 6. We can search for a solution to this congruence in the simplest way by trial and error. If x is equal to 0, we don't get a solution. 1 doesn't work. 2 times 2 is 4, which is not congruent to 5 modulo 7. 3 times 2 is 6, which is congruent to 1 modulo 7. That doesn't work. 4 times 2 is 8, is congruent to 1 modulo 5. 5 times 2 is 10, is congruent to 3. And 6 times 2 is 12. And sure enough, 12 is indeed congruent to 5 modulo 7. So this is solved by x is equal to 6, and of course anything that is congruent to 6 modulo 7. And that is a solution that we find simply by trial and error. Let's try the next one. 2x is congruent to 3 modulo 4. Now when we're working modulo 4, we need only consider possible solutions 0, 1, 2, and 3. 0 clearly cannot work. 1 likewise will give us 2 times 1, which is congruent to 2 modulo 4. 3 times 2 is 6. 6 is also congruent to 2 modulo 4. And 4 is itself congruent to 0. We've run out of possibilities. So what we find in the second case is that 2x is congruent to 3 modulo 4 has no solution. So we can see that some such problems have solutions and some of them do not. Furthermore, in this case, as long as we're working with integers modulo 7, there's only one solution that works here. Here, of course, there are none at all. Now, these are two examples which illustrate the claim of Theorem 3. If the greatest common divisor of a and m is equal to 1, and of course m is greater than 1, then ax is congruent to 1 mod m has a unique solution. If that is the truth, if that is the case, it will also allow us to solve the linear congruence ax is congruent to b modulo m for any b that we might choose. Now, just a quick definition: if ax is congruent to 1 modulo m, then we say that x is the multiplicative inverse of a in the ring Z sub m. We denote this by the notation x is equal to a inverse. Another much less common notation is that x equals a with a bar over the top. We probably read that as a bar. The meaning is the same. This is a much less common notation. However, it is used in our current textbook, and therefore we won't be able to avoid it. So let's see if we could find a proof for this statement here. If ax is congruent to 1 modulo m and has a unique solution if a and m are relatively prime. Well, if the greatest common divisor of a and m is equal to 1, there have to be integers s and t satisfying this statement. 1, the greatest common divisor of a and m, is equal to s times a plus t times m. Now, what we want to notice is that if we were to subtract t times m from both sides, we would have s times a is equal to 1 plus t times m. But of course, since t times m is a multiple of m, this is congruent to 1 modulo m. Thus we see if a and m are relatively prime, then S times A, where S is the coefficient of A that we obtain by using the extended Euclidean algorithm, is a multiplicative inverse of A modulo M. And that completes the proof. Let's take an example of that then. Suppose that we were interested in solving 2x is congruent to 1 modulo 7. Well, all we need to do is to use the Euclidean algorithm to express 1 as a linear combination of 2 and 7. In this case, that's particularly easy, so we can skip the Euclidean algorithm and simply write down the answer. Minus 3 times 2 plus 1 times 7 is equal to 1, which tells us that minus 3 is an inverse of 2 modulo 7. Now, of course, minus 3 is probably not the form that we want. Minus 3 is congruent to 4 modulo 7. Therefore, 4 should act as a multiplicative inverse of 2 modulo 7. Let's try it. 2 times 4 is 8, which is indeed congruent to 1 modulo 7. Now, this allows us then to solve the linear congruence. Let's go back to the example that we worked earlier. We found that x equals 6 is a solution to 2x is congruent to 5 modulo 7, and this solution was found simply by trial and error. We have now a multiplicative inverse of 2 modulo 7, which means that we can solve this in a more systematic way. 2x is congruent to 5 modulo 7. We have a theorem that allows us to multiply both sides of this congruence by any integer we choose, and so we will choose the integer 4 since it's a multiplicative inverse of 2. 4 times 2 is 8, which is congruent to 1 modulo 7. 4 times 5 is 20, which is congruent to 6 modulo 7, and this is the solution that we obtained last time by trial and error. Thus, we know that if the coefficient of x is relatively prime to the modulus, there must be a multiplicative inverse of the coefficient. We multiply both sides by that multiplicative inverse, reduce modulo m, and we'll have the solution no matter what our linear congruence was that we started with. Let's take another example of this. Suppose we want to solve 3x is congruent to 2 modulo 7. Well, we first note that 3 and 7 are relatively prime, therefore a solution must exist. We'll start with 3x is congruent to 1 modulo 7. If we can find a multiplicative inverse of 3, then we'll be almost finished. 5 times 3 is 15, and 15 is congruent to 1 modulo 7. Therefore, 5 is the desired inverse, and just to check, 5 times 3, 15, is congruent to 1. X equals 1 times 5, or 5, is the multiplicative inverse that we seek. The inverse of 3 is equal to 5 modulo 7. Then we can take our original congruence, 3x is congruent to 2 modulo 7, multiply each side by 5. 5 times 3 is 15, which is congruent to 1. 5 times 2 is 10, which is congruent to 3. And we see that x equals 3 is a solution. Let's just check that. 3 times 3 is 9. 9 minus 7 is 2. Sure enough, 3 is a solution to this original congruence. There's a related problem and a theorem called the Chinese remainder theorem. My sources indicate a variety of dates for when this question was first found in the ancient Chinese literature, so let's just go direct to the more entertaining of the presentations of the story. A gang of 7 bandits stole a bag of coins. Upon trying to divide it between them, they found 2 left over. In the ensuing fight over the remaining coins, 2 of the bandits died. They tried to divide the coins among them again, but this time there were 3 left over. Once again, remaining 5 bandits fought, and another 2 of them died. This time 2 coins were left over, and the question is, how many coins are in the bag? The problem can be restated as a system of linear congruences, and we state and solve it as follows. First of all, we know this. A gang of 7 bandits stole a bag of coins. Upon dividing it between them, they found 2 that were left over. Therefore, x, the number of coins in the bag, is congruent to 2 modulo 7. Well, after the first fight, 2 of the bandits died, 5 of them remain, and this time there were 3 coins left over. Finally, they fought again, and another 2 died, so that 3 are left this time, and 2 coins are left over, so that x is congruent to 2 modulo 3. The question is there any x in the integers such that x is congruent to 2 modulo 7, 3 modulo 5, and 2 modulo 3? The answer is yes, and it's not difficult to construct the answer if you know the trick. Let's first review something just from algebra though. A corresponding algebra problem may be something like this. I'm looking for a polynomial equation that has these features. First of all, if I take f and evaluate it at 7, I get 2. If I take the same function f and evaluate it at 5, I get 3. The same function f evaluated at 3 is equal to 2. Can I find the function? The answer is yes, and Lagrange gave one clever solution to this. We're going to express this polynomial as a sum of 3 quadratics, and we'll do them in a way that's possible to build them up without a lot of calculation. I'm going to leave a little bit of room here for a coefficient, but then I'm going to say this. The first quadratic polynomial is going to be composed in part of x minus 5 times x minus 3. The second part, leave room for a coefficient, is going to have factors x minus 7 and x minus 3. The last one will begin with coefficients, will begin with polynomials of x minus 5, x minus 7 rather, and x minus 5. Now what I'd like to do is make sure that when I evaluate this polynomial at 7, it will yield 2. You should notice that there's an x minus 7 in this term and an x minus 7 in this term, so no matter what these coefficients are, if I were to evaluate this polynomial at x equals 7, I'll get a 0 from both of these terms. On the other hand, this one will not be 0. When I evaluate it at 7, this factor will be 2, 7 minus 5, and this factor will be 4, 7 minus 3. So this is 0, this is 0. As this is written right now, it would be equal to 1. So if I multiply this by 2, I will ensure that f at 7 is equal to 2. In the same way, if I evaluate this function at 5, this term will be 0, this term will be 0, this is the only non-zero term. At 5, this factor is 5 minus 7, this factor is 5 minus 3, and now as it's set up, if I replace x by 5, I'll get a 0 here, a 0 here, and a 1 here. Multiplying by 3 ensures that f at 5 is equal to 3. Finally, using the same trick, this coefficient 2 comes from here. I'll be interested in this when f is equal to 3, so I replace x by 3, 3 minus 7, 3 minus 5. This is known as the Lagrange interpolating polynomial. Now we're not so much interested in interpolating polynomials at this point in time, but we just want to notice the trick that we've split this function into 3 parts in such a way that 2 of its 3 terms are going to be 0 whenever we evaluate at 7, 5, or 3, and the remaining term has simply been cooked up in such a way that it would be equal to the 3 functional values that I seek. I'm going to do the same thing now to try to solve this system of linear congruences. We're going to set this up in a way that's very similar to the way we solved the interpolation problem with Lagrange interpolation. We're going to have factors of 5 and 3 in the first term, because that means that this term will be congruent to 0 when we evaluate modulo 5 or 3. Likewise, 7 and 3 here means that this term will drop out when we evaluate modulo 7 and 3, and likewise this will drop out if we evaluate modulo 7 or 5. Evaluating modulo 7 then, only the first term survives. Modulo 5, only the second term survives. Evaluating modulo 3, only the third term survives. Our goal is to find 2 different coefficients to put in here in order to get these congruences to be satisfied. So let's begin by evaluating modulo 7. Firstly, the second 2 terms will be congruent to 0 since they have factors of 7. Let's concentrate now on the 5 times 3. 5 times 3 is 15, which is already congruent to 1 modulo 7. Therefore, this first coefficient can be simply a 1. Now, if we evaluate modulo 7, a 0 is contributed by these terms, and at this point we have a 1. We would like this term to be congruent to 2 modulo 7, so we multiply it by 2, and this is the form so far. We'll now proceed. We have determined that 2 and 1 are these two coefficients. We need to determine the next 4 coefficients. Alright, now we'll be looking modulo 5. The first and the last term are congruent to 0 modulo 5. Let's take a look at the middle term and first concentrate on the 7 times 3. 21, once again, is congruent to 1 modulo 5. Therefore, its inverse is 1, and our first coefficient is 1. We want, however, x to be congruent to 3 modulo 5. We multiply this term by 3, and so far we have this sum. The first term we did by evaluating modulo 7, the second evaluating modulo 5. We'll now proceed to evaluate modulo 3 to determine the two coefficients on the third term. The first two terms will be congruent to 0 since they have factors of 3. 7 times 5, or 35, is congruent to 2 modulo 3. Therefore, we will need to find an inverse other than simply putting a 1 here. 25 inverse then is the same as the inverse of 2, and in modulo 3, 2 is its own inverse. That's because 2 times 2 is 4, which is congruent to 1 modulo 3. So the 2 goes in. We now need one more factor here to ensure that this x is congruent to 2 modulo 3. Multiplying by 2 takes care of it, and so far we have this sum. This is congruent to 2 modulo 7. The others are congruent to 0 modulo 7. This term is congruent to 3 modulo 5. The others are congruent to 0 modulo 5. And finally, this last term is congruent to 2 modulo 3. The others are congruent to 0 modulo 3. This can be simplified, of course. Multiplying and adding, we get a total of 233. It turns out that the smallest solution can be found by reducing this modulo 7 times 5 times 3, the 3 moduli in the congruences we're trying to solve. Doing that, we get 23. All solutions then have this form: 23 plus anything that's congruent to 23 modulo 105, and so this is our full set of solutions.